Hello everyone and welcome to our last YouTube video today. We are going to be doing the final section, chapter 6C. So chapter 6C is going to be about normal distribution. So first we're going to define normal distribution. A common type of distribution is represented by the bell-shaped curve, formerly called normal distribution, which is a symmetric bell-shaped curve with a single peak. Generally, that peak corresponds to the mean, median, and mode of the distribution. And it does also have some conditions. A data set that satisfies the following criteria is likely to have normal distribution. Number one, most data values are clustered near the mean, giving the distribution a well-defined single peak. Second, data values are spread evenly around the mean, making the distribution symmetric. Third, larger deviations from the mean become increasingly rare, producing the symmetric tapering tails of the distribution. Symmetric tapering. And last, individual data values result from a combination of many different factors, such as genetic and environmental factors. Okay, which of the following best represents normal distribution? Well, if we're looking, we can see that this one here, letter A, has this nice bell shape, and letter B has this kind of skewed data. So we would say A best represents normal distribution. Next, we want to talk about variation. So we can have high variation or low variation, and generally that just means how far away the data is spread from the mean. So you can see here on letter A, the data in the curve is pretty largely spread out. But here in letter B, the data values are relatively close to the mean. So you would say A has greater variation than B does. Okay, let's do our first example. Which of the following would you expect to have a normal or nearly normal distribution? Well, scores on a very easy test. If you think about it, if the test is very easy, that implies that the mean would be high, like close to 100, which implies we would have left skewed data. And then part two, foot length of a random sample of adult women. Well, we do know that foot length is a human trait, so we expect the lengths of feet to cluster near a mean and become less farther from the mean in both directions, which would give the distribution a bell shape or be a normal distribution. So we would expect this to be bell shaped. Okay. All right, next we will talk about the standard deviation and the z-scores, or I'm sorry, the standard normal distribution and the z-scores. So generally we talk about if we have the mean, our data is within 1, 2, or 3 standard deviations of it on either side. So if it's left of the mean, it is negative. And on the right of the mean, it is positive distance. Okay, so this is standard deviation. So then we'll go into how to compute the standard score, which is also called the z-score. So the number of standard deviations a data value lies above or below the mean is called its standard score or its z-score, and it's defined by this equation: z equals standard score, which is data value minus mean divided by the standard deviation. So the first question is, the Stanford Binet IQ test is designed so scores are normally distributed with a mean of 100 and a standard deviation of 16. Find the standard scores for IQ scores of 95 and 125. So first, we know that the mean is 100 and that the standard deviation is 16. And then you want to find standard scores for the IQ scores of 95 and 125. So for the first part, that means our data value is going to be 95. And if we peek back up here at our equation, we'll have z equals data value minus mean. So that's 95 minus 100 divided by the standard deviation, which was 16. 95 minus 100 is -5. And then we would need to do the -5 divided by 16. And you should get -0.3125. So that is the standard score or the z-score. They are the same thing. Okay, next we want to find when the data value is 125. So we plug it back into the formula. So we get 125 minus 100 divided by 16. 125 minus 100 is 25. And then you would just need to do the 25 divided by the 16. .5625 will be your standard score. Okay, moving on. So now we'll talk about percentiles. So the nth percentile of a data set is the smallest value in the set with the property that n% of the data values are less than or equal to it. A data value that lies between 2 percentiles is said to lie in the lower percentile. And then, for example, if you scored in the 45th percentile on the SAT, what that means is 45% of SAT scores are lower than yours. So 45th percentile, 45% lower than your score. Okay, so let's go through this example. Cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178 and a standard deviation of 41. In what percentile is a man with a cholesterol level of 190? So we know that we have Z is going to be equal to 190 is going to be our data value. Our mean is 178. Then we divide by the standard deviation, which is 41. And then the first thing that we'll do is the numerator. So 190 minus 178 is equal to 12. And then we divide by 41. I got 0.292. I'm going to round it to 0.29. And then we want to figure out what percentile is that. Well, what we're actually going to do is use this really, really nice table right here on the next page. So since we got negative 0.29, we're looking here down at the z-scores, and we can see that there is no negative 0.29. There's a negative 0.25 and a negative 0.3. Since negative 0.29 is closer to negative 0.3, we will use that score. So we look at negative 0.3, we see 38.21, which means 38.21 percentile. So scroll back up. So we get 38.21. So it's just using the table. Okay. What cholesterol level corresponds to the 90th percentile? A 90th percentile. So we're actually looking for the data value because it wants to know what level. So first thing that we're going to do is look and see what is the z-score of the 90th percentile. So if we zoom in over here on this side of the table, you see percentile, and it says 90 right here, and then you see z-score, and it says 1.3. So that means we're going to have our z-score is 1.3 equal to, and we're looking for the data value because we don't know the cholesterol level, that's what we need, minus the mean, which was 178, divided by the standard deviation, which was 41. And now we solved for the data value. So the first thing that we're going to need to do is multiply by 41 on both sides. So we'll have 53.3 is equal to data value minus 178. And then we'll add 178, add 178. You should get 231.3. Which means that the cholesterol okay. All right, next. The standard scores on a psychology exam were normally distributed with a mean of 67 and a standard deviation of 8. About what percentage of scores were above 59? So this is tricky because now it's asking for above. And we know that percentiles always show us below. So we'll have to do some manipulating here. So first we'll do finding the z-score. So z is going to be equal to 59 minus the mean, 67, divided by the standard deviation, 8. And again, always do the subtraction in the numerator first. So we have 59 minus 67 is a negative 8. Divided by 8 is going to be negative 1. And now we are going to scroll up and look for where we have negative 1. It's right here. A z-score of negative 1 means you're in the 15.87th percentile. So Z equals 15.87, but that means that 15.87% were below 59, because that's what percentiles mean. Since we want to find out how many was above, we're going to do 100 minus 15.87. Because if 15.87 were below, that means the rest have to have been above. So you get 84.13%. So y'all need to make sure you're paying attention to when the question is asking for above versus below. What percentage of scores were below 83? So we'll have Z equals 83 minus the mean, which is 67, divided by the standard deviation, which was 8. And then 83 minus 67 is 16. And 16 divided by 8 is 2. So if we scroll up to our table and we look for this 2, a z-score of 2 is 97.72. So that means this is going to be 97.72% were below 83. Because the percentiles always give you what is below. All right, let's go through some examples. State whether or not you expect the following data sets to be normally distributed and explain. The distances between the bullseye of a target and 100 darts that are thrown by an expert. So the key here is to notice that we are looking at distance. So, and it's an expert. So if you're having an expert do what they're good at, they're likely going to be very close to the target. So, and very few away from the target. Okay? So if we were to draw this little L, where this is a distance 0 away from the target, distance of 1, 2, 3, 4, etc., you would expect them to all be relatively close to the target, maybe a few right at 0, but all relatively close because they're experts. And then kind of teeter, maybe they had a bad moment and had a bad shot. So we'd actually expect this to be right skewed. Next, scores on an exam. We weren't given that the exam was easy or difficult, so we can assume that it was a moderate exam. And generally, test scores tend to have a bell curve shape. All right. Example 6. Use the table to find the standard score and the percentile of the following data value. A data value, 1 standard deviation above the mean. 1 standard deviation above. So that means Z equals 1. Scrolling to our table, what happens when Z equals 1? We get 84.13. Next, a data value with standard deviation 0.5 above the mean. Okay, 0.5. So we scroll back up to our handy dandy table. We see that 0.5 corresponds to 69.15. So 69.15 percentile. Lastly, a data value with 1.5 standard deviations below the mean. Now remember, if it's below the mean, that means the z-score is negative. So we'll have z is equal to negative 1.5. Then we scroll back up And we can see negative 1.5 corresponds to 6.68. All right, that concludes our lesson today on 6C. Thanks so much for tuning in, and I hope y'all have a wonderful rest of the day.